Now that we know about local and absolute max and minimums, we can think to ourselves, okay, when can we guarantee that some of these values exist? So that leads us to this next section, which is the extreme value theorem section. So this is an important theorem in mathematics, and it's shows up here in calculus. So this is really giving us conditions for a function f that are going to guarantee that the function f has an absolute maximum and an absolute minimum, right? So there are some situations where these values don't necessarily exist, but this theorem gives us two conditions under which the function is definitely going to have an absolute maximum and minimum. Okay, so if we read closely the extreme value theorem here, it says if f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in AB. Okay, so this is really saying if your function is continuous and it's defined on a closed interval from a to b, then there are going to be two x values that I can plug in. One of them is called c, one of them is called d. Two x values inside of that interval from a to b, and I can plug those in, and one of them is going to give me an absolute maximum, and the other one is going to give me an absolute minimum. Okay, so this theorem is guaranteeing the existence of an absolute max and minimum given that f is continuous and it's defined on a closed interval from a to b. Okay, so these graphs are some examples of situations you might get into. So the first one, you can see, so this is defined on the closed interval from a to b, and the absolute maximum, so you can see this is a continuous graph. There are no breaks, no holes, anything like that. So an absolute maximum happens here at c, and the value is f of c, and an absolute minimum happens here at d, and the value is f of d. And you can see, one thing I want to point out is that this value c and d, these both happen inside of the interval from a to b, right? So they live somewhere inside of that interval. You also might have a situation like this second graph. So here the absolute maximum happens here at c. So here's f of c. Okay, and that is within the interval from a to b. But this time, the absolute minimum happens right here, right? Which happens to be an endpoint, right? So here, this d value is actually the same as b. Okay, so it's possible that your absolute maximum or minimum comes not from being inside of the interval like it was here, but really from somewhere on the endpoints, right? And we saw this come up in one of the previous examples. Okay, so here the absolute minimum is attained at one of the endpoints of the closed interval. Okay, and then another thing that might happen is you might end up with something like this next graph where you have an absolute minimum here at d with value f of d, and actually you have two places that give you an absolute maximum, right? So there's no reason why you can only have one. You might have more than one. You might have infinitely many. So here, if we plug in f of c, if we plug in c1, if we plug in c2, we get f of c1, and that happens to be the same as f of c2, right? So these are both going to give me an absolute maximum. Okay, so you might have more than one. Okay, so now let's talk about these two conditions, right? So if you look at this theorem, it's saying the function has to be continuous and it has to be defined on a closed interval from a to b, right? These are the two conditions that are going to guarantee that there exists an absolute max and min. Okay, so let's look at what happens when we don't have one of those two conditions. What might we get into that makes it so that we don't necessarily have an absolute max or min? Okay, so that's these next couple of examples. So, like I was saying, so you need both that the function be defined on a closed interval and that it be a continuous function. Okay, so here we have a graph and an equation for a function that is not continuous. Okay, although it is defined on a closed interval. Okay, so it's defined on the closed interval from, so you can see you start drawing the graph here at x equals 1, or x equals minus 1. So its domain is really from minus 1. And you can plug in any other number all the way up to here at x equals 3. So its domain is from minus 1 to 3, right? And you can see you can pick any point from minus 1 to 3. I can plug it into this function and it will have an output, right? So it is defined from minus 1 to 3. Okay, so this is defined on a closed interval, but it's not continuous, right? And you can see that it's not continuous because of this break right here. Okay, there's this jump discontinuity. Okay, so let's see what happens, right? So if we think about what are, or maybe slash is, the absolute mins. I'm saying plural because I already know that it's going to be more than one of them, right? So if you look at this picture, you can see absolute minimums are going to happen right here at x equals 0 and right here at x equals 3, right? Because the rest of the graph lies above these 2 points, okay? So we are going to get these. So we have absolute mins so we have 2 of them this time. So we have one at x equals 0 and one at x equals 3 with value. So they have to have the same value, right? So here both of their value is 0, right? Their y value, okay? So that's great, right? So this function does have absolute minimums, right? In fact, it has 2 of them. But let's think about what happens when we look at absolute maxes. Okay, so you can see here the situation isn't going to be as nice. So if we think about where should the absolute maximum be? Well, the highest point should really be somewhere right here, right? So we really wish that this point right here would be our absolute maximum. However, there's really no x value that we can plug in that's going to give us this y value of 2, right? So you might think to yourself, okay, this should be the absolute maximum, right? But then you're wondering, okay, what do I put in here, right? What is the x value that I can plug in that's going to give me 2, right? That's going to give me this y value. And really, if we plugged in, so you might think maybe 1, right? Maybe I can plug in 1. But if you plug in 1, you can see it's actually filled in right here, and it's not filled in up here, right? So if I plug in 1, it's going to give me this output right at 1, rather than this top one at 2. Okay, so that is where we run into a problem, right? Because of this discontinuity, there's no x value that I can plug in that's going to give me a y value of 2, and that's really where the absolute maximum value should be. Okay, so you might think to yourself also, what happens if I just plugged in something that was very, very close to here? Okay, so something very, very close to x equals 1. Well, if you plugged in something, so if you plugged in anything as close as you could get to here, maybe you plugged in some number here, right? So some x value, maybe the x value that goes with this point, we'll call it c. We'll call it c. But then I could always plug in something right around here. Maybe we'll call that a. And then that would really no longer give you an absolute maximum, right? So maybe I plugged in a, right? Okay, so now you might have thought this was an absolute maximum, but it's not because of this a, right? So this a is actually now giving you a higher y value, right? So the y value was here, whereas now I could plug in a and it gave me this y value. There's always going to be another number that I could have plugged in that would give me a higher f of x value. Okay, so this function really doesn't have an absolute maximum. Okay, and that's because it's not a continuous function. Okay, so that shows that this continuity requirement is really essential, right? We need it. We absolutely need it. Okay, so let's think about the other condition, right? The idea that we need a closed interval. Okay, so that's this next example. So if we look at this function, so this is the function g of x equals, so this is a line. This is the line with slope 1/2. And it's defined on the interval from -2 to 2. Okay? So you'll notice this is a line, so it's a continuous function. We know lines are continuous. But it is defined on an open interval. Okay? So because of these parentheses, rather than the hard brackets, this is an open interval, meaning that we don't include the endpoints. Okay? So you can see right here and right here, we're not including those endpoints. Okay? So if you think to yourself again, what is the absolute min and what is the absolute max for this function? Well, the absolute min, you really want it to be right here at x equals -2, and you want the value to be -1, but it's not, right? Once again, there's no x value that I can plug into here that's going to give me, nope, not 3, question mark. So there's no x value that I can plug in that's going to give me this y value of -1. Okay, so there's nothing that I can plug into here that's going to give me that. And similarly, there's really no x value that I can plug in that's going to give me this y value at 1, right? Which really should be what the absolute maximum is, right? But there's really nothing that I can plug into here. Okay, so that really shows you that, okay, it's fine if I have a continuous function, but in addition to that, I do need it to be a closed interval, because if it's open, it allows for things like this to happen, right? Where we have a number that should be the absolute max or the absolute min, but there's no way of getting there, right? Because we can't plug in these endpoints. Okay, so now you try out this next example.